It's good.
Awesome. Okay, hello everybody. Welcome to spring 2021. One more weird semester. Hopefully this is it, but we're going to have fun with it. So make sure you're in the right place. You had to click like 14 times to get here, so I assume you're in the right place. But this is 6.832 Underactuated Robotics. We're going to do it a little different this time, because we're on Zoom and because the world's moving fast and there's all these good things happening. So let me spend the first few minutes sort of telling you our approach to teaching this way. I want to get your feedback early and often, including at the end of the lecture today. But part of this is I've started using slides.com, which is, you see it on the screen here. I just said it a minute ago, but if you just joined, I recommend you take that URL and put it in your browser and follow along that way. I think Zoom will let you still see our faces on the side, but if you watch the slides via your browser, then I can download not only robot videos, but so like YouTube videos will go directly to your browser and play at full frame rate. I can inject simulation into your browser. It's been a while figuring that one out, but it's pretty cool. All kinds of sort of interactive features that I can stick directly into your browser if you just open up that URL. All of it should be available on the screen here too, but it's just less fun. Some of the other ones you can actually interact with. Okay, so let's get started. I'm Russ, by the way. We have an awesome course staff. Dongchan, if you want to raise your hand.
Hi, everyone.
Hi there. Dongchan he works with Professor Slotine. He's a controls expert and will bring a real nice depth in sort of mathematical controls and optimization to the class. AJ is in two places, but one of them can wave. Yeah, AJ. AJ is our computer science, I'd say, expert, but he also works with Songbei Kim, and so if you've seen Mini Cheetah or the humanoids that they've been working on, he's your man to tell you all about that kind of stuff. And then Eric is just below him on my screen. Hey, Eric. Eric is working with Poolkit. He's our sort of resident reinforcement learning expert. If you want to understand how the ideas we're talking about here connect to some of the RL stuff, which we'll actually talk about a ton. But Eric will be an expert for you to bounce ideas off there. Super happy to have everybody signed up, and because we have such a good, strong course staff, we've been thinking about how to interact with you as much as possible and make sure you get face-to-face time with all of us, because that's more fun for us too. The website there, you probably found on your way here. The root website is the course notes, and you can hang a spring 2021 off it to get to the course website. All the lecture notes are there, and on the course website is all of the material you'll have, including our grading policy and all the assignments and links to Piazza where anything else might be. Good. So I really want these lectures to be interactive. This is actually the first little widget. It's not the most exciting simulation, but it is a simulation that is now being sent to your browser. It takes a minute to load because I didn't optimize the meshes of the KUKA. They're kind of stupidly big to be sending over the internet, but anyhow, this is you can play with this, right? So this is a 3D simulation that you can interact with. This one's just running through a script, but we'll have much more interesting things to do with our simulation going forward. And this is a part of the way I've been trying to innovate on teaching over Zoom, is a way to make live experiments via simulating robots in your browser. So we'll see if we can make good on that, and I'm very much open to ideas. Piazza, presumably you got here via Piazza, so you know about that, but the goal is to have everybody who's registered for the course on Piazza. Our underactuated staff is the main way to get all of us. Of course, you can email us individually. The lectures like this, which are the sort of the main lectures, we're going to put on YouTube. People tend to follow along with the course. I love it, and people comment on YouTube, and I try to answer, and it's been fun to watch the way people interact with us on YouTube. We also have the textbook has the ability to, I put some JavaScript on the textbook so that you can annotate it as if you're on Google Docs, sort of. And there's a little etiquette page you can click to. I'll show you what it's about here. But there's a bunch of ways that you can get a hold of us, either Piazza or the YouTube channel or the annotations. And all of these are my attempt to interact with you despite the distance. I really do love seeing people's faces. Not everybody wants to do it. I don't. It's okay if you don't want to, but just know that I love it. So I mean, for me, one of the biggest challenges of teaching remotely is that I think people don't realize how much, like when I'm writing on the chalkboard, even if I spend a lot of time kind of looking this way, I lecture differently because I'm reading the room, and it's little facial expressions that people make. I can tell if people got it or didn't get it. I need to slow down. I need to speed up. I need to say that one completely again, right? Some people get a lot, me included, get a lot out of reading the room, and it's no fun talking to the black wall. Okay, so yeah, so feel free to like talk. I mean, that's a normal thing. You can talk, you can unmute, you can talk. Chat is fine. I'll try to keep it open now that I said that. Make sure it's open on this screen. Yeah, anything you can do. I guess I forgot to put on raise your hand on this, but I'll do that for next time. And anything we can do to sort of make that more interactive. And we'll make sure. So I am pinned, just so you know, if you become Zoom experts, I am pinned. That's why I'm highlighted in green. So only I will show up on the YouTube stream. So you can say things and your face won't appear or anything. Awesome. Okay, so the textbook is interactive also. It's kind of fun to think about. I actually started thinking about this way back when Apple announced iBooks 2, which never really took off, but it was such a good idea to have like these fully immersive, interactive textbooks. And I started thinking, how can I make our textbook more interactive? And so as you go through the textbook, you'll see lots of elements. So first of all, this is actually the textbook here. You'll see videos are embedded. You'll see more interesting things as we get in with simulations and other things embedded. You'll also see at the top of every textbook page, this open and collab badge. Almost every chapter in the textbook has a collab notebook, which you'll have plenty of experience with soon if you haven't tried it before. It's a Jupyter notebook that runs on a Google server. And so the way I imagine people reading the textbook is sort of clicking that link when you start a chapter, it opens up. It takes like 2 minutes to provision the cloud machine. So you just click that. And then when you start scrolling and you get to an example, there's a link that goes into the subframe, of that. So it's ready for you. It's all queued up and ready for you. You can do your interactive experiments as you read. And those will be the same tools that we'll use for your problem sets too. The other thing I'll point out here now is that, see this, this thing here, there's a, sometimes people catch me on typos and edits, and those are cool too. Although I do have a special way to tell me about typos. This one says I explained it better in lecture. That's great. I mean, so there's like a conversation we can have on the notes, and people write all over the place, from all over the place, and ask some great questions, right? So feel free to mark it up if that's useful. You can write it to PDF too if you want, but I sort of optimize it for the online experience. So I'm an optimist. I think that there's a chance that we can actually do more interesting things. We can actually teach you better over Zoom than I can in person. It's missing, of course, some of the social cues, and my gosh, I don't know. I was so tired by the end of the semester last time. I guess maybe all of you were too, but it's got its flaws. But there's one thing that it gives me that I never had before, which is that every one of you has a browser open, and I can inject code directly into your browser, right? That was something I never assumed I could do in class. And so that means I can do simulation experiments with you during lecture. And I'm going to do things like that throughout. I'm just sort of, we're all exploring the space together of how to do this right over Zoom. I'm very open to suggestions, changes. I'll give you lots of opportunities to give me feedback, but never be shy about reaching out and just saying, hey, this worked great, this one, not so much. And there's a lot of, emerging understanding of what is working and what isn't working, and what causes burnout, what doesn't cause burnout, and the social interactions that people miss the most. There's some great literature emerging now. Okay, so in that spirit, the biggest thing I want to try this week, I sort of consider it an experiment of 1 week. And if it works, great, we can do it for the rest of the semester. If it doesn't work, it's very easy for me to go back to the normal lecture format. But I would like to do kind of a flipped format. I think the numbers play out so that we can spend actually quite a bit of time with you if we divide it up right. So I'm conscious of not taking more than the allotted time. You'll see my strategy for this week. You can give me feedback. Let's see how it goes. So I have, in the fall, I tried teaching all over Zoom, and I was teaching a new course and I didn't have any content. And so I tried a bunch of things. This semester, it's a slightly different case because I do have recorded lectures from a previous term. So the way I'd like to try it this week is to give you this short, fully synchronous lecture. Just spend about 30 minutes of your time here. Ask you to watch the lectures for the week online. But then we'll, on Thursday, do kind of completely interactive thing, which I've never been able to do with people before. And we can break you up. So I think let's see, I think the ratio, depending on how the enrollment changes over the week, but I think we could be and if nobody shows up, then it could just be me. But if everybody showed up and we have the enrollment about what it looks like, then it's going to be pretty small groups of good ratios of staff to students. And the goal would be to bring up one of the rich experiments from the problem. We're going to include it on the problem set in case people can't attend the synchronous lecture. So it'll be like a problem that everybody does, but please come and do it with us. We'd like to talk you through it. We'd like to, teach you some of the stuff around it, some of the context, we want to hear your questions. We want to hear your different systems that are similar. Can we think of it the same way? That's what this is intended to do. So we'll do via Piazza once the enrollment kind of hits a steady state. We'll assign out 30-minute slots during the normal lecture time. And so the thinking is, you're watching almost an hour and a half lectures. And so that really should consume the time you've committed to lecture for the week. But maybe you're watching me at 2x. I won't take it personally. I'm going to squeeze in just 30 minutes of your time on the lecture days if I'm asked you to watch the online lecture, and hope that counts out. And the reward of sort of interacting with us more, sorry if that's not a reward, but hopefully that works out to be pretty reasonable. I'm going to ask your feedback all the time for that, so please tell me what you think. If you can't make the synchronous session, like I said, it will be on your PSET. So it's not, I'm not mandating that people must make the normal time, but I would love it if you do. That's the way we get to see you, get to see if you're getting it, get to tune the course as it goes. Here's another little experiment, since we're in the experiments. I don't know if anybody who took manipulation with me last fall. Lecture 1 included a similar experiment where I found out there's a user limit to the whiteboarding app that I had planned to use. So I see people drawing, that's success, right? So it looks like it scales. Nobody's getting error, user limit exceeded or anything like this. Sweet. So I'll find a way maybe so people don't draw on top of this too much on top of the slides. But it's an open source project that I'm going to contribute to if it looks like it works. So, okay, success. All right, what's Underactuated Robots all about? Based on the YouTube hits, the number of views, I have to guess that you've already seen this video. This is in some ways, I mean, it's maybe the best video ever made by a roboticist ever in history, right? It also represents in kind of a deep way the culmination of everything we've been talking about in this class for a number of years. There's much more going into that robot than what we've talked about in class, but actually the people that are behind the screens there, some of them are former TAs of this class, and it's just like, this is kind of what the class is all about. I mean, it can have different impact on the world than just dancing, but somehow the beauty and elegance of this working is kind of what the class is all about. I will insert a blank slide so that people pay attention. Actually, so there's a couple other things besides just the sort of mathematical dynamics and control and computer science control that we'll talk about in the class. For instance, actually, those robots are just spectacular. They're marvels of design, right? So the power to weight ratio that they've achieved at those robots, some of those moves, you know, I thought for a second, wait a second, that doesn't look physical. You know, could that possibly be real? They wouldn't release an edited video, right? You know, it looked almost aphysical. And that's just because they've reached a regime where they are able to produce more torque, speed, you know, power at the joints than any animal we've ever watched. And so it just doesn't look normal sometimes. Like some of those moves with its feet are just, you know, beyond what a human could do, right? A human might do other things better, maybe, but the hardware is pretty darn impressive. And the fact that it is so robust, right? That those robots take a beating, they get back up and they dance again. And that's how you get to success like that. But there's a lot of really, really good dynamics and controls behind there too. And that is what we're going to talk a lot about in the class. Now, it's interesting, as I've, you know, all my friends emailed me the video, my family, that, you know, people I haven't talked to in years, they're like, oh, have you seen the dancing robot videos? And I'm sure that was happening to you guys too. One of the interesting things I noticed, almost everybody I talked to, at least all the computer scientists I talked to, they would say, oh, this robot video was awesome. But then they would say something like this, you know, it's really impressive, but it's kind of, you know, it sounds like it's not using learning. Like, what's up with that, right? So, and in fact, Scott and Mark, two of the main folks behind that robot, gave an excellent talk at one of the machine learning conferences, the NeurIPS conference last December, of talking about why they didn't use machine learning as much as you might think and some of the challenges there. But this is actually super interesting to me and super deep. And I think I want to actually, to the point where I want to spend some of the semester talking about it, right? I want to talk about the approaches to learning that could work here, and why some of them don't work as well here as you might think. And I want to walk that line and really explore some of the most recent advances in machine learning, compare them head to head with some of the approaches that you see on that robot and we've been talking about in the past. And that's going to be a big part of our conversation this semester. So I'm going to leave a lot of so if you've looked at the notes before or something, you have expectations for the course, those expectations I think will be met. You will see the core dynamics and control and planning machinery that I love to talk about in this class. And it is an explicit goal for me to teach computer scientists about dynamics and robotics, right? And teach mechanical engineers about some of the CS algorithms and just cross-pollinate in general. But I want to actually carve out some time. I took some of the lectures and set them aside and said, we're not going to cover this time, so that I can take a deep dive into some of the newer topics in learning models, okay? And then doing planning and control with learned models. So that means there'll be some more classical lectures. Well, we'll see. I could give them however we're working best together, but new content for sure on some of the ways you might learn a model that looks like the models we're already using on Atlas, a physics-based model, learning just purely data-driven models. And you might think, if you've thought about these ideas before, you might think linear models, that's not going to get me very far. Well, you might be surprised actually how far it will get you, but that's not, I don't actually think they're going to get us all the way, but I think there's just a beautiful clarity that we can get by thinking about linear models that we won't be able to get in the more complicated models. So I'm going to stick in some, let's understand how it works in the linear case. We'll talk about if we have a deep network as a model, what does that give us? We know there's great tools out there for training deep network models. We're not going to emphasize that, but we'll walk you through that. And I want to emphasize that if someone gives you a deep learning based model, then how do you do planning and control with that model? Okay. And there's really good, interesting ideas coming out nowadays about how do you, what state estimation should imply about the model you build, and how do you make models that are relevant to the task but ignore distracting things that could be happening in the background, things like that. Contact in the robots that touch the world and make contact with the world, which you'd like to think every robot should do that, right? But that it produces a whole new bag of interesting challenges. So that's going to get its own lecture, its own treatment about how do you do control with mechanical systems making and breaking contact, like the Atlas was doing, and like any system that's doing manipulation or other sort of cool robots. So another name for this, I would say, is you could almost think about it as we're gonna do a deep dive on model-based reinforcement learning, right? And one of the things that's happened a lot in the reinforcement learning literature is that it spiked in popularity. Everybody saw some things it could do that looked amazing, and there was kind of a recoil where people started saying, well, things that are based purely on data might have limitations in terms of sample efficiency and the like. And there was a renewed interest in people using reinforcement learning ideas to learn a model first and then do control on the model. Now, that whole story continues to evolve. People have, I think the purely model-free setting has moved forward again when people are talking about batch, offline, RL. I think there's a rich conversation there. But there's other classes even this semester. Poolkit is teaching a class, Kathy Wu's teaching a class that are talking about the more model-free reinforcement learning. The thing we're going to focus on here is the model-based version, where we're going to talk about, I love dynamics. We're going to talk about the dynamics. We're going to understand if we have particular models that have structure, like structure you'd expect to get out of a dynamical system governed by Newton's equations. How do you exploit that structure in your algorithm, right? So that's where this algorithm, that's where this class sort of shines or focuses compared to some of the other offerings. And I'll take any questions about that online or offline. Okay, so model. What do I mean by model-based control, right? So when we have an Atlas in the lab at MIT also. This was the older version of Atlas. This was, I guess, version 1, and it was much heavier and much less powerful, but still awesome and robust. We spent a long time with this robot, and all of our control, all of our balancing control and walking control and the like, was based on models, right? So we started off by writing the equations governed by rigid body mechanics, and then we developed controllers based on those models. And so it's interesting when people say it's a little disappointing that the robot doesn't use learning. So if you dig a little deeper, then it's like, okay, what's wrong with using the models? I think that there's a couple concerns that people might have. One is that I think people worry that models based purely on physics could be limited. It's not even just physics, it's like a particular class of it. We chose to model this link and this link and this link and this link. And therefore, if something different happens, it's out of the model class, and so I won't be able to model it. And I think that is a valid concern, and we'll talk about that. The most extreme view of this is I guess Rich Sutton sort of is the famous person for saying it. He says, basically anytime you inject any human designed attribute into the algorithm, you've put a limitation in by the limitation of your own mind is constraining what the robot will ultimately do. So there's value in that discussion, and we'll talk a lot about it. I think the second concern is that learning, of course, means improving, or the ability to improve, hopefully. And if it's not learning, it won't continue to improve and adapt as it goes through the world. So let's talk about those quickly. So let me just be clear on what I mean by a model. So what I have if I'm observing the robot, right? I have some inputs to the robot, which are my commands that I send to the motor. Those are I call those U for the rest of the term. I'll call those U. And then I have some outputs, which are the sensors that I'm reading from the robot, which could be joint sensors, it could be cameras, it could be lots of things. Those are Y. And that's, the world, all I get to see about the world is the input-output data. But we choose to try to build mathematical models that summarize in a compact form that input-output data relationship, right? And they come in many forms, right? Some of you will be very familiar with these equations. Some of you less familiar. We will They will be old friends by the end of the term. But I think I can make a point that should, I hope, land even regardless of your familiarity. There's a type of model here, which is the state space model, where I specifically make a vector to represent the current state of the robot. I use W to talk about noise and disturbances, and I use theta to talk about parameters. So I can have, this is like a differential equation. This one's a difference equation because it's discrete time model that can describe the evolution of that. And if I've calibrated that well, it can describe the input-output behavior. And actually, that's not the only type of model you see. When you see people in reinforcement learning, for instance, learning models that take a history of observations, like a history of images is my state. That's not quite right. What they're really doing is more of an autoregressive model, and we'll talk more about the differences here. But just to say, there's a few ways we could write down a mathematical model for the input-output data. And we should understand that I think, in the state space form, we still have a couple choices. We have Lagrangian mechanics kind of choices, or we have neural network kind of choices that both land in this sort of state space world. And we can do, people often do feed-forward networks in these autoregressive kind of models. But those are not, I think I wanted you to understand that whether you're using Lagrangian or recurrent networks or whatever, these are somehow orthogonal to some of the other important questions about data efficiency and the like. And then, so if we've got this model now of just we're fitting mathematical equations to describe the input-output data, then I'd say the choice of the function f and g, that's what describes the model class, okay? And if it's not until I set a particular set of parameters that now I've got an instance of that model class. So when people talk about should we use deep learning or should we use physics-based models, what I hear is that that's a question about the model class, right? What is the class of functions we should use to describe our system? And that's a good question, and we'll dig into it, right? Should we prefer writing F using physics or deep networks? If you choose physics, there are some advantages because we know a lot about it, but there are some disadvantages. It might be limited. We might have made some assumptions that don't hold as the world changes. But it's really not that different, I think, than having the discussion about should we be using rectified linear units or Tanch units or LSTMs or transformers, all of the things you hear about in a neural network course, okay? And in fact, people are increasingly putting pieces of Lagrangian mechanics into the networks alongside some of the other typical neural network architecture elements. But I want to point out that the distinction is not right off the bat about data. And in fact, our most precious mechanics folks, the ones who gave us the physics equations, right? They were all data scientists. So that, maybe Einstein not so much, but like, so, the beginnings of it was all about doing experiments and then trying to summarize those experiments with simple equations, right? And they fit actually very noisy data. Like I kind of wonder sometimes whether the fact that they had noisy data forced them to have simple models. Maybe we're hurting ourselves by having such beautiful sensors, but it seems remarkable that they were able to do so much with such noisy data. And what they gave us was this super rich class of parametric models that we can now fit to data, right? So if you choose for F and G to use the equations recommended by these folks, then you're just making a choice of model class, and you can talk about how do you find the best fit in that model class and how do you control with that model class. Or you can use a neural network, and that's a different model class, and we now have new tools to fit data to that model class that are working incredibly well. I can't help but think, like, if we had done these experiments, back in the 16 and 1700s, and the output of that was like a 1.3 megabyte, file of weights matrices or something like that, where would we be today? There's something I think to be said of somehow compressing the data into the most minimal form that neural networks are not doing for us today. And I think that manifests itself in some of the ability to make control harder, but it's a fun thought exercise. But no doubt there's problems that we want robots to do today, like as we get robots that are doing food preparation and all these other things, if you think about what would Newton have written down for this, it makes my head explode because it's got a lot of different equations flying around, and the number of equations is changing every time the knife hits the cutting board and stuff. So I fully admit that there are problems we want to control with robots. They shouldn't be off limits, but they feel constrained by the fact that we're using physics-based equations. So, my take on it is, I think these are both valid concerns. I think the models based on physics may be limited. That one I really, I do think a lot about. The second one I push back on a little bit, just because I think if you're using the model-based approaches we tend to talk about, of course, you should continue to improve those models with data, and people have always done that. And I don't think it's correct to say that we're ignoring data if you have a physics-based model. So my view is that I think each model class has advantages and challenges, and let's meet for why don't we meet every Tuesday, Thursday for a semester, and we'll talk about it. We'll talk it out. All right, so I promised to keep it short today because I really do want to respect the total amount of time that you've allocated to the class. This is the basic plan, right? So please make sure you're on Piazza. You probably got here through there. Watch this week's lecture video. Now, there is one evil thing I'm sort of doing here, which is I don't know how to give an exciting breakout sort of interactive session on Thursday if you haven't watched the Thursday lecture yet. So if you can get ahead of it just this 1 week, then I promise I won't be asking you to front load things. But this is the sort of, to do the first session, it would really help if you could watch Thursday's lecture before 1:30 on Thursday. Not totally required, but please take a look at the lecture notes, leave comments, send feedback. Problem set 1, we're going to give you a bunch of 5 problem sets over the term. They're already on the calendar. We are going to do our level best to hit those, keep those deadlines real. The first one will be released tomorrow. There's a midterm on the calendar, and the final projects in this class tend to be awesome, really a lot of fun. Start thinking now about the kinds of systems, the kind of robot you might have behind you, or you might have never touched a robot, and we'll help you find your favorite simulation of a robot. But people have done some really fun things in the class. I remember AJ did a humanoid doing a backflip, and his friends before him did the mini cheetah doing a backflip, and that stuff's just awesome, right? All details, including the grading policy, are on the course website. So every time I talk, I'm going to ask, there's every once in a while I forget to put up the last slide, but always I have this little thing in the slide. And if you have it in your browser right now, it's super easy, I hope, to just click and tell me, what do you think about continuing to participate in lectures synchronously, and anything you've seen. I don't want to give you the impression that I've never asked this before. I've been asking everybody for a year now what's working for flipped classrooms and the like. Available to have traffic, yeah. I'll take any reasons you can give me. The link still works, good. Yeah. Oh, so this should totally work. You can type right in there. This website it's as if you opened up Google Forms right there. You can click right on that website. It's a live form, and you can hit submit at the end. And that's all I'm asking. And anything you can give me to sort of share your experience about flipped classrooms and what you'd like to see out of this. I really want to spend time with you and the staff, or I really don't want to spend time with you and the staff. I just want to hear it, and it's anonymous. So just let us know. I will stop talking now, again, out of respect for the time, but I will hang out here and happy to answer any questions or talk or whatever. And I would ask you then to watch the version with the whiteboard and the full version of the first lecture, which will help you understand how much and why I love dynamics. And we will see you on Thursday. We'll announce those times.